Control systems is the science of making machines behave the way we want them to behave as opposed to how they would naturally behave. It is sometimes referred to as the hidden technology, because it is all around us, from the oven to rockets and of course in cars, but nobody really speaks about it unless problems arise, which is fortunately rarely because it is a very successful technology. But what do we mean by systems and control? Systems have inputs and output signals, and a behavior that evolves over time. Systems can be broken down into components, which are something that we think we understand. In physical systems, inputs are generated by actuators, for example, DC motors or LEDs. Outputs are measured by sensors, for example, cameras or wheel encoders. These sensors produce observations. Controlling a system means to design a logical component that will output, at every instant in time, the commands for the plant actuators, so that the output of our system follow a given plan. The main objective of the controller is stability. Stability can be summarized as things don't blow up. Mathematically, we can formalize the stability with a notion of bounded input, bounded output, or BIBO stability. If a bounded input is provided as input to the system, then the output of a stable system is bounded too. In other words, if finite energy is provided to the system, then finite energy should exit the system. When math tells us infinite energy, it is a way to say that things blow up. There's no such thing, in fact, in the real world as infinite energy. Guaranteeing stability alone does not imply that the system will perform well. Performance can be measured in several ways. For example, how quickly does the system converge to the plan, or how precisely? Other performance metrics might be the maximum acceptable error at any point in time, or how well can the system recover from unexpected external stimuli, such as the noise in the measurements or disturbances, like a sudden gust of wind or hitting a bump on the road. Robustness, instead, is the ability of the controller to provide stability and performance even in the presence of uncertainty in the mathematical model of the plant. What if the wheels of the robots are slightly of different sizes, or the disposition of mass is different than what assumed? What if instead the parameters of the system just change over time because of wear and tear, for example? A robust controller would handle these cases well, despite the uncertainty. Robustness and performance are trade-offs, and striking the right balance is a challenge that really depends on the application. With these objectives in mind, stability, performance, and robustness, we can start now thinking about the structure of the controller. The simplest approach is for the user to send a predetermined sequence of commands directly to the actuators. This is called open-loop control. If our understanding of the platform response is good, we will obtain the desired outcome. If it is not good, or if something unexpected happens during the execution, then the end result will diverge from the plan. In open-loop control, information flows only in one direction, from the controller to the plant. To enable the controller to take into account the actual execution, we could close the loop by feeding the sensor measurements back to the controller, creating a feedback loop. Feedback control is very powerful because it allows the whole system to adapt to circumstances as they are unfolding and apply corrections on the fly. The measurements themselves, though, generally need to be processed before being fed back to the controller, as they might include a lot of redundant data straight out of the sensors. How to structure this agent is up to the designer, to us. We could use different approaches, for example, a deep neural network trained from real data or simulation to translate the images from the camera directly into commands to the wheels to keep the ducky butt on the road. Traditionally, agents are designed with three main components: perception, planning, and control: to see, to plan, and to act. The perception block is responsible for transforming the data from the sensors into actionable information for the robot. This passage is sometimes called filtering, or estimation too. These estimates of relevant quantities, for example, the position or the orientation of the robot's reference frame with respect to the world and the other objects in it, represent what is the robot's belief of his current state. This belief might be more or less corresponding to the truth, depending on the quality of the measurements and the perception solution used. The planner, instead, provides a reference path for the robot to follow. For example, between two nav points in a more general task of reaching a goal position while avoiding obstacles on the road. The planner receives the state estimate as input, so it can adjust the nominal plan on the fly. The plan and the state estimate are finally fed into the actual controller, which uses them to compute a decision applying a certain logic. For a DuckyBot, the decision of the controller will be a sequence of commands, which will be sent to the motors, finally closing the loop.